Okay, so let's see what this problem asks for. So we've got a man here at B, and he's pulling on this cable at 30 pounds, and we want to determine the magnitude of the force F that this man over here at C has to exert to keep the pole from rotating, which means the resultant moment about A is 0. That's actually something in the next chapter we're going to enforce along with our equations of equilibrium, is that typically for an object to be in equilibrium, not only the sum of the forces have to be 0, but the sum of the moments at points have to be 0. So this is kind of a prelude to that. So all we have to do is write the moment of this force P, which we know to be 30, about A, and set it equal to this force. So I'll start with the force P. So what is the moment of force P about A? There's a couple of different ways to solve this. The way I'm going to do it is like we've talked about in class, is I'm going to break it into components. So I'll have a X component and a Y component. What's the great thing about my breaking it up into components is that my Y component is going to pass through A and create no moment. So I just need to find the X component and multiply it by the total distance, which is 12 plus 6, or 18. So that moment, I'll say the moment about A, is going to be equal to this Y force, which is P, times, doesn't matter which angle you choose, which value, cosine 45, and the distance is 18 feet. Now in this case, since P is 30, someone's going to have to get out of their calculator and tell me what that value is. I don't know what that is off the top of my head. Yeah, and then times 18 to go ahead and get me the total moment. Everybody else get that? Yes? So 382, and that's going to be pound-feet for the units. So now also the moment about A, do this guy over here at C, and what's he going to have? Also, he's going to have a Y force and an X force. One thing I should have mentioned is that about A, this force P is creating what kind of moment? If we're using counterclockwise, it's positive. Yeah, so I'll go ahead and put my sign convention there. So this is a positive moment. The other about A, again, if we're assuming positive, so we're going to get this force, the horizontal force here will be 4/5. So I'll have 4/5 of the force F times its moment arm, which is 12 feet. And that's going to be a negative. So those things must balance. So if I actually sum my moments about A and make sure they're 0, I would get 382. And over here I would get minus, let's see, what's that? I'll just do it this way, 48 divided by 5F. And those all have the units of pound-feet. So you can solve for F. So what is F? It should be 382 times 5 divided by 48. What do you get? Anybody? 40? Exactly? Okay. 39.7. Sounds reasonable. Anybody else get that? Huh? That seems okay. Why does that? I think that's reasonable because the man here at B has a longer moment arm, right? So he has a smaller force. So a smaller force times a larger moment arm. This man over here at C has a shorter moment arm, so he has to pull at a larger force. So logically it makes sense. Hopefully we didn't make any calculation mistakes. The other interesting thing here is you could find the Y components of these forces and determine if your pole can handle that additional force. You don't want your pole to buckle or fail. That's beyond us. We could easily sum these two forces up and find out if our pole is going to survive. So any questions about that? I kind of like that problem. I thought it was just an application of some of the things we've been doing.